Okay, yeah, that works. All right, so do you guys have any questions? I made an announcement yesterday. So yeah, I think the video I did for week 2, lecture 1, something happened that didn't get uploaded, but it should be up now. Were you guys able to open it?
Yeah, I was able to open it.
You were able to?
Yes.
Okay. Yeah. And if you guys need more time for homework, I shifted some quizzes so they're due a little bit later. And then the homework for like the publisher homework, MyLab, there are due dates, but they're more like guidelines for you guys. So if you don't finish that on time, you can still work on it like without any penalty. All right, so kind of like due dates are so you know when you should kind of complete those homework assignments, but if you don't do it on time, you can still keep working on them. That make sense?
Professor, I had a quick question. It says though on the homework, I think it mentioned something about like the score being reduced by 1% each day that it's not completed by the due date. So is that not correct?
Yeah, I'm going to change it. I think I forgot to change it on like one of the first assignments. I'll change it. Yeah, you can. It's not going to be reduced. It's just you can keep working on them.
Okay, thank you.
Yeah, I didn't change it yet, but I will after class today. Yeah, because I mean, it's better if you guys do those homework problems late than not at all. But again, it's just kind of on you to be responsible enough to like not fall behind too much, right? Just because it's not, necessarily due at a certain date doesn't mean, because to prepare for quizzes, it's good to do your homework, right? Questions? So we'll continue today. I shifted topics a little bit, so we'll finish 1.4 today and start 1.5. Hopefully, finish 1.5 as well. So that would be your week 3 material. So we'll see how far we can go, and then I'll, like shift the dates if we need to. All right. But last time, so we did this last time, so a little bit of review, right? So we did the definition. If I have some vectors in Rn, right, then the set of all linear combinations of those vectors is going to be called span of those vectors. And remember, linear combination was basically taking some constants, right, maybe alpha1 multiplied by vector v1 plus some constant alpha2 multiplied by vector v2, right, and so on, all the way to some constant alpha p multiplied by vector vp, right? So I'm basically taking a sum of some constants multiplied by different vectors. And this is called my linear combination. So linear combination. Right, so I'm basically taking a sum of different multiples of different vectors. That's my linear combination. And if I want to look at all of the possible values of my constants, right? So alpha1 is any real number, alpha2 is any real number, right? And so on. So all of those different sums for all of the different values of constants are going to be called the span of those vectors, right? And the span of those vectors is called the subset of Rn span generated by V1, V2, Vp, right? So just some new jargon for you, right? Some terminology. So we'll kind of talk about linear combinations of vectors and spans. So kind of you guys are familiar with it, right? So the span of vectors is a collection of all vectors that can be written in the form, right? This is basically my linear combination. We're using C's instead of alphas. Right, and C1, C2, Cp are just some scalars. So and we did a few things last time, right? We talked about how basically there's different ways to look at it. If I have a vector B and vector B lies in the span of those vectors V1 to Vp, this is equivalent, absolutely equivalent to saying that an equation, right, constant V1 plus constant V2 and so on equals to B, right? So B in the span of vectors V1 through Vp is equivalent to saying that B can be represented as a linear combination of those vectors. Or in other words, that equation, this vector equation has a solution. And both of those statements are also equivalent to saying that the augmented matrix, if I put my vectors in the span here as columns in my matrix, and the last column is B, my augmented column, if this augmented matrix has a solution, then this is equivalent to saying that this equation has a solution and B is in the span of V1 and Vp, right? So I mean, the more you do this, it becomes more intuitive, but it's good to kind of get comfortable with the idea that all of those statements are basically saying the same exact thing, just kind of phrased a little bit differently in mathematical terms, right? Because when we're solving this equation, we're basically solving for values of the variables like C1, C2, all the way to Cp, right? So if I was to rewrite this equation in the matrix form, I mean, this would basically be my augmented matrix with the augmented column B. Does that make sense, everyone? So I kind of did this last time, and we'll do some more examples today, so everyone's comfortable with this. And I will talk a little bit more about like matrices and how to form those sort of matrices here. Any questions so far? That's good. All right, so one example, right? I have two vectors, A1, right, with three components, right? So you can say, kind of, again, learning terminology, that my A1 belongs to R3, right? So three-dimensional space. My A2, another vector with three components, so it also belongs to R3, three-dimensional space. And I have another vector B, again, three components, so it means it belongs to three-dimensional space R3. Right, and in this vector B, I have one variable, so it's 4, 1, and H, and I don't know H. So one question is, for what values of H is B in the plane spanned by A1 and A2? Right, remember last time when we were talking about span, so this is in 3 dimensions, right? So in 3-dimensional space, I'm looking at this. If I draw my vectors A1 and A2, right, they basically define a plane through the origin, right? So if I kind of imagine like the flat surface that connects A1 and A2 and extend it in all the directions, the span, right, span of my vectors A1 and A2 is going to be plane through the origin. Right, so I'm kind of geometric representation of the span of two vectors in 3D, right? And from kind of the previous setup, what do we know? If I want to know if my vector B lies in a plane spanned by those two vectors, I'm basically asking a question, well, is my vector B, I mean, somewhere over here and lies on that plane, right? But in other words, if B belongs to span of A1 and A2, right, we have 3 different ways to look at it, and we're going to look at it the way that's easier for us to deal with, right? So I can't directly answer this question if B belongs to span, but I know how to form my augmented matrices and how to kind of solve my linear systems. So instead of kind of answering this question directly, what I'm going to do is I'm going to look for a solution of my augmented matrix where I have my two vectors spanning the plane as my first two columns, and my augmented column is my vector B. Right, I'm just kind of using this equivalence here. Does that make sense? Yeah. So, all right, how do we form augmented matrix? I have my first column, A1, so 1, 4, minus 2. My second column, A2, minus 2, minus 3, and 7. And my augmented column comes from this vector B, so 4, 1, and H. All right, so this is my augmented matrix with columns A1, A2, and B, right, basically. And I'm just solving it with my elementary row operations like we did before, right? I have my first pivot, 1. I need to eliminate everything that's below 1, right? So I'm going to do my row 2 minus 4 row 1 to eliminate 4, and my row 3 plus 2 row 1 in order to eliminate this minus 2. All right, and you can do kind of this wiggly line, or you can do arrow, right? It doesn't matter, just as long as it kind of makes sense that I'm going from this step, I'm doing these operations, And what I'm going to get here when I complete those, right, I'm going to get 1, minus 2, and 4, right? I'm not doing anything to my first row. In the second row, I'm taking 4 minus 1, minus 4 minus 4, minus 3, minus 4 times minus 2, and 1 minus 4 times 4, right? And so on, just doing those elementary row operations. So I'm going to get 0, 5, and minus 15. And in the last row, right, I'm going to get 0, 3, right, and over here I have h, which is a variable, and it's okay, I'm just gonna leave this as a variable. So I have h in my row 3 plus twice the value in row 1, right? So h plus twice 4 is 8. No? So, okay, then kind of going further, right, this is my first pivot. In my second row, 5 is going to be my pivot, right? And I mean, I have to do something with my second and third row, but maybe just for simplicity, I'm going to rescale things a little bit. So I'll take my second row and divide it by 5. Right, the values are going to be pretty nice here. And I'll take my third row and divide it by 3. Right, just kind of rescale so it's easier to kind of add and subtract my rows, so I don't have to use fractions. Really kind of the only reason I'm doing this now. Right, so after rescaling, I'm going to have first row is the same, minus 1 or 1, 2, 1 minus 2, 4. Here I have 0, 1, minus 3, and then 0, 1, and then I have my h plus 8 divided by 3. I just rescaled a little bit. So, and then again, I'm using my pivots. This pivot in the second row, so I'm going to eliminate everything below. So I'm going to have my row 3 minus row 2. All right, so it's a lot easier to subtract. All right, so when I do this, I'm going to have what? I have 1 minus 2, 4, like I had before. Then I'm going to have 0, 1, minus 3. And over here, I have 0 minus 0, 0. 1 minus 1 is going to be 0. And then I have h plus 8 divided by 3 minus 3. Right? Plus 3. Right? So what's going on here? I don't know what h is, but I want to know for what values of h is b in the plane spanned by a1 and a2. So I'm looking for values of h for which this augmented matrix has a solution. So what could go wrong here, right? For a matrix to have a solution, this has to be consistent, right? So it must be consistent. So what could go wrong here? All right, I mean, I have my first pivot column, second pivot column. I mean, nothing really crazy going on here. So, I mean, I know that my variable x2 will be equal to minus 3, right? My variable x1, I can solve for it in terms of x2, right? So x1 will be equal to 4 minus, or 4 plus 2x2, right? And I know what my x2 is. But the only thing that could really go wrong and give us no solutions is if this value here not equal to 0, right? So if I look at this, h plus 8 divided by 3 plus 3. If this equals to 0, I have the entire last row of zeros, which is fine, right? Because I'm basically getting 0 equals to 0, so system is consistent, right? But if this value is not equal to 0, I'm going to have an issue, right? Because remember, in matrices, when I have any one of the rows having 0, 0, 0, and some non-zero value, right? So maybe I'll put this here. So 0, 0, 0, and some non-zero value, right? And maybe I have 0, 0, 0, and 3, something like that. in the augmented matrix, when I translate it to something, this would basically be 0 equals to 3, which is false. All right. So for this case, in order for my system to have a solution, I need to make sure that this here is not equal to 0. Or that this here equals to 0. Does that make sense? So if this is not equal to 0, then my system is inconsistent. And I have no solution. Right. So really what I want here, in order for my vector B to lie in the plane spanned by A1 and A2, I need to have this case when h plus 8 over 3 plus 3 equals to 0. All right, so I want h plus 8 over 3 plus 3 equals to 0, or h plus 8 equals to minus 9, or h must be equal to minus 9 minus 8, or minus 17. That makes sense?
Professor, I had a quick question.
Hmm?
When we are asking if the vector B is an element of the span of A1 and A2, are we asking if B can be written as a linear combination of A1 and A2?
Yeah. So all those statements are equivalent. So if the vector is in the span of other vectors, this is equivalent to saying that I am able to find a solution, or in other words, constants A1 or C1, C2, Cp, such that B can be written as a linear combination of those vectors. Absolutely equivalent statements, just phrased differently. And also absolutely equivalent to kind of forming augmented matrix from those vectors with B as my last column. If this matrix has a solution, this basically means that I am able to solve for constants C1, C2, and Cp, such that B is a linear combination. That makes sense?
Yes, thank you so much.
So again, same kind of, just have to get used to kind of looking at it 3 different ways, but it's really same exact thing, right? B is in the span is equivalent to saying B can be represented as linear combination of those vectors. And B being able to write B as a linear combination of those vectors means that if I solve this as an equation, I am able to find solutions, right? So if I'm doing it in the augmented matrix form, this augmented matrix has a solution. Yeah, makes sense? All right. So then here, that's how we basically solve for H that would allow us to place B in this plane spanned by A1 and A2. All right, so I can do another example here. All right, so here I have matrix A, 3 columns, right? So I'm going to call them like A1, A2, A3, and I have a vector B, right? So again, 3-dimensional. So I'm going to define the space W as span of columns of the matrix A. So I'm just taking it as a kind of, this is my A1 vector, A2 vector, and A3 vector. So span of those 3 vectors, or span of columns of matrix A. And again, I'm asking the question, is B in the span of those 3 vectors, right? So, and again, you're going back to your kind of, those 3 statements are completely equivalent. B is in the span of the columns of A if my augmented matrix with B as an augmented column has a solution. So again, just to answer this question, you have to go to your augmented matrix form, right? So you'll take your A, again, 2 minus 1, 1, 0, 8 minus 2, 6, 5, 1. Augmented column is B, 10, 3, 3. All right, so this is basically my augmented matrix with columns A1, A2, A3, and B. All right, does this have a solution? If it has a solution, then B is going to be in a span of columns of A. All right, so how are you guys doing on like elementary row operations? Doing all right? All right, so again, I'll just rescale first. So row 1 divided by 2, just so it's a little bit easier to kind of do my subtractions. All right, so then I will have 1, 0, 3, 5. I'm just rescaling. The other two rows the same, -1, 8, 5, 3, 1, -2, 1, 3. Now, start with your first row. What is my pivot? My pivot is this first position here. I want to eliminate everything below. So I'm going to take my row 2, -1, so row 2 plus row 1, and row 3 minus row 1, right, to eliminate those values. So when I do those operations, I'm going to get 1035, right? First row is unchanged. Then I have 0, 8, 8, 8. And I have 0, -2, -2, -2. I'm just doing my elementary row operations. So again, I can rescale a little bit. I can divide my row 2 by 8 and row 3 by -2. Right? They're basically all just ones here. So if I rewrite everything, I have in my augmented matrix 1, 0, 3, 5, 0, 1, 1, 1, 0, 1, 1, 1. Right, I just rescaled. I have my pivot in the first column, I have my pivot in the second. Oh, pivot in the first row, pivot in the second row. So I want to eliminate everything below this second pivot. All right, so again, I'll just do my row 3 minus row 2, right, to eliminate 1. And I'm almost done. 1, 0, 3, 5. I have 0, 1, 1, 1. And everything becomes 0. Right, because I basically have the same two rows. Right. So what am I getting from this? Well, this whole row of zeros doesn't really give me much information. This is just, right, 0 equal to 0, right? So, I mean, I should have a solution. And I have pivots in column 1 and column 2, right? So if I start translating it into kind of my values of variables form, this will give me my basic variable x1 or c1, whatever you want to call your solution set. Because I have pivot in the second column, this will give me my basic variable x2. I don't have a pivot in the third column, so I know that my variable x3 is going to be free variable. Because I have no pivot in the third column. I mean, this is fine. It just basically means I'm going to have infinitely many solutions, right? But I do have solutions, just not a unique one. So and then express everything in terms of x3, right? So x2 is going to be equal to 1 minus x3. And x1 equals to 5 minus 3x3. Right? So everything is expressed in terms of my free variable x3. Right? So I can write down my solution. I can do it in vector form, or, well, I mean, let's just do it in the same way that we did before. All right. I have my solution set x equals to, that x1 is 5 minus 3x3, x2 is 1 minus x3, and x3 is just x3. All right. So provided my x3 is any real number, this is my free variable. That makes sense? So, but I mean, to answer the question, is B in the span of those three vectors? I mean, yes, because, I mean, not only I can find one solution, I can actually find infinitely many solutions, right? So if I'm writing down the linear combination, x3 can be any real number, so pick something easy, maybe let x3 equals to 0 or something. So then my solution set is 5, 1, and 0. Right, this vector satisfies my system. So that means that I can write down my vector B as a linear combination of those three vectors. Right, my first constant is 5 multiplied by A1. Second constant is 1 multiplied by A2. And third constant is 0 multiplied by A3. But that's fine, right? I can have a 0 constant. There's no problem. All right, so my B equals to 5. A1 is 2 minus 1, 1. All right, plus 1 times A2. A2 is 0 8 and minus 2. Right, so this is my linear combination. That makes sense? And I mean, you can check, right? 5 times 2 plus 0, 10. 5 times minus 1 plus 8, 3. Right, 5 times 1 minus 2, 3. Right, so this equals to my B. That makes sense?
Professor, I had a quick question.
Yeah.
How do you know when to tell between whether you have a system has a solely like a unique solution versus a infinitely many?
Well, I mean, you do have to do this elimination process, but once you get to at least like row echelon form, the way to know is looking at your pivots. So if you have a pivot in every row, then you're going to have a unique solution. But if you don't have a pivot, like over here, I did not have a pivot in my third row or third column, right? Because kind of like those first 3 columns are the columns of my matrix, and this is just the augmented column. If I had pivots in every row, that would mean that I only have one solution. But if I'm missing some pivots in some rows, like over here, I'm missing a pivot in the third column, in the third row. That means that my third variable is going to be a free variable. Like I don't have a constraint on it here. So it could basically be anything, any real number. Yeah, so basically you have to look at this, the pivot columns. If I'm missing a pivot in the column, that means I'm going to have a free variable there, and free variable means I'm going to have infinitely many solutions. That makes sense? I mean, we'll talk about it in a second too. I'll have like a theorem about it. But
Thank you
does
so much.
kind of make sense conceptually, at least? Yeah.
Yeah, it definitely makes sense. Thank you.
Yeah, because I mean, we had infinitely many solution because that third row just turns to 0, right? I don't have a constraint. Because I mean, in general, if you have 3 unknowns, you need some kind of 3 conditions or 3 constraints, right? But here, what we're getting is that, I mean, I kind of do have 3 constraints for 3 variables, but it turns out that my kind of 2 of my rows are actually kind of give me the same exact information. So it's really just 1 constraint and not 2. Make sense? All right, so next one. So let's kind of start looking at it a little bit. Well, it's pretty much the same thing, but well, again, it's just different way to write things that may be a little bit more convenient for us. So just something to get used to, but we're not really doing anything different. We're just kind of writing things down in a slightly different notation. So what we want to do is we want to write our linear systems, not just kind of in terms of span or augmented matrix form. We're going to write them down in terms of what's called the matrix equation. So the definition is, if A is an M by N matrix with columns A1 all the way to AN, so columns defined by those column vectors, and X is some vector in Rn, all right, so N components, then the product of A and X, we call it AX, is the linear combination of the columns of A using corresponding entries in X as weights, right? So we'll talk more about matrix multiplication, but this is basically kind of like the beginning of learning how to multiply matrices, and also the reason of why we define matrix multiplication a certain way. Because, I mean, originally, what did matrices come from? Basically to solve linear systems. And a lot of the algebra of matrices kind of was defined because this is how it's easier for us to solve linear systems, right? So basically here we're defining a multiplication of M by N matrix by a vector in Rn by basically taking values in my vector X and multiplying them by corresponding columns in A. All right, so I'm gonna, for example, what I have here. So this is my vector X, and this is my matrix A, right? And I have my columns, right? This is my column A1, this is my column A2, this is my column A3. Right? So I'm defining my multiplication by right, I'm taking first component x1 and x4, and I'm multiplying it by first column, 1 and 0. Then second component in x3, and I'm multiplying it by second column, 2 and minus 5. And then lastly, the last component of x, right, 7, and I'm multiplying it by the last column in A, minus 1 and 3. Right, does that make sense? And then we can go further, right? We know how to multiply scalars to vectors. Multiplying scalars to vectors, I'm basically multiplying both components in my vector by the scalar. So 4 times 1 and 0 is going to be 4 times 1, 4 times 0, right? Plus 3 times 2 and 3 times minus 5, and plus 7 times minus 1 and 7 times 3. All right, so multiplication of scalar by a vector. I'm basically multiplying each component. Right, so I'm going to get 4, 0 for this vector. Next vector is 3 times 2, 6, and 3 times minus 5, minus 15. All right, and the next vector I have plus, plus minus 7, right, and 21, 3 times 7. Right, so now I'm adding 3 vectors, and with addition of vectors is going to be component-wise. 4 plus 6 minus 7 for first component, 4 plus 6 minus 7, and 0 minus 15 plus 21. So if I compute everything, 4 plus 6 minus 7 is 3, and over here I'm going to have 6, 21 minus 15. Right, so we basically took a matrix, multiplied it by a vector, and we're getting another vector. Does that make sense? So, and one thing to notice here is, what do I have here? I have a 2 by 3 matrix, right? And I'm multiplying it by 3 by 1 matrix, right? So my first dimension is how many rows, how many columns? 3 rows, 2 rows, 3 columns. 3 rows, 1 column, right? So 2 by 3 multiplied by 3 by 1. So when we start doing matrix multiplication, this is going to become important, because in general, you can only multiply 2 matrices when your inner dimensions here agree, like those two has to be equal. And then the result of your multiplication is going to be your outer dimension. So 2 times 1, at the end, I'm getting 2 by 1 matrix. All right, 2 by 1, and I can only multiply if I have 3 by 3. Does that make sense? So we'll get back to this, but it's kind of, if you start like forgetting what to multiply by, and your matrix is like m by n, like it will be kind of a reminder of what to multiply.
So is
Mhm.
it the number of columns in the first matrix needs to be equal to the number of rows in the second in order to multiply? Is that what that is?
Yeah, because what I'm doing here is I'm taking, those are my x values, right? I'm basically taking those x values. So this goes here, then this will go here, and this will go over here, right? So this is my x1, this is my x2, and this is my x3. And I'm multiplying them by my columns, right? I have my A1 here, A2, and A3. So number of columns in my matrix must be equal to the number of elements in my vector, because I'm doing element by column. That make sense? Yeah?
Yeah, it does. Thank you so much.
Yeah, so I can do another example here. So again, I'm multiplying here a 3 by 2 matrix by 2 by 1 vector, right? And I'm always just thinking what I'm taking. This is my vector x, so I have x1, and I have x2, right? And those are my 2 columns here, column 1, column 2, right? A1 and column A2. All right, and I'm just doing x1 times A1, so 4 multiplied by my vector A1, which is 2, 8, and minus 5. Right, and then plus x2, which is 7, multiplied by the column vector minus 3, 0, and 2. And that makes sense. X1, X2, and this is my A1, this is my A2. All right, it's like written over here. Makes sense? And then you can continue just using your properties, right? Scalar multiplication by a vector, right? I'm going to have 4 times 2, 4 times 8, and 4 times minus 5. All right, so I have 8, 32, and 20. All right, 4 times minus 5. And then 7 times minus 3, 7 times 0, and 7 times 2. I'm going to get, right, minus 21. 7 times 0, 0, and 7 times 2, 14. All right, and the last step, I'm adding 2 vectors. Vector addition is just component-wise. So 8 minus 21, 32 plus 0, minus 20 plus 14. So I'm going to get my vector minus 13, 32, and minus 6. All right, so, and I'm getting, as I would have predicted, 3 by 1, 3 components, 3 rows, and 1 column. All right, 3 by 1 result. That makes sense? Not too bad. All right, but again, I mean, the hardest part about linear algebra is just getting used to kind of a new way of kind of looking at things, because when you do algebra, and when you did calculus, I mean, it's not really how you do things. You're just dealing with kind of functions of real variables. It's always just scalar quantities. But now we're dealing with those kind of new mathematical objects where we have vectors and matrices. So you just have to get used to kind of doing the algebra for that, and otherwise it's not that complicated. Again, the hardest part is just to get used to those new notations and those new algebraic operations. Like, we know how to multiply 2 numbers together, but here I have not just numbers, but like a matrix and a vector. So how do I multiply a matrix by a vector? So you just have to remember the rules for doing algebra on those objects. But once you kind of get comfortable with it, it's going to be a lot easier. All right, so let's do another example here. So suppose I have 3 vectors in R3, right? And I want to find the linear combination as a matrix times a vector. So again, it's just kind of practicing writing things in different notations, right? So if I want to write, so if this is linear combination, again, you can always go back to your kind of equivalences, right? Something in a span equation has a solution where it's basically be written as linear combination or augmented matrix form. And now we're also adding this kind of matrix equation set up to this. So, but I mean, okay, I have 3 v1 minus 5 v2 plus 7 v3. Right, and I want to write this as a matrix times a vector, which is basically just going in the opposite direction, right? I had constant vector, and so on. I can basically take all my vectors together and form a matrix out of it. And then all of those constants in front, I can kind of pack them away into this vector form, right? So again, it's basically just going out in the opposite direction. I have 3 v1 minus 5 v2 plus 7 v3. Right, and just think of it as, you know, this is my x1, this is my x2, and this is my x3, right? So what I'm doing is I'm taking my x1, x2, and x3 and packing them away in this vector, and then I'm taking those vectors v1, v2, and v3 and just forming a matrix out of them, right? So if I take v1, first column of the matrix, v2, second column of the matrix, v3, third column of the matrix. And then I'm just taking my x1, x2, and x3, and I'm kind of packing them away in my vector. So first component 3, second component minus 5, and third component 7. So this is my matrix A. Right, with 3 columns formed by vectors v1, v2, and v3. And this is basically my vector x. All right, so Now I have rewritten it in the form A times X. Right? So again, kind of linear combination form and matrix equation form. Right, again, same thing, just different ways to write this. Right, this is a linear combination. Form. And this is my matrix times the vector form. So it's just, again, it's just notation. How do you write this? And I mean, depending on what you're doing, one way could be kind of better than, sometimes it's easier to look at something in terms of linear combination. Sometimes it's easier to look at something in terms of matrix times a vector. Right, but we're just starting with linear algebra, so we want to be kind of comfortable with all of the different ways of writing things. So, kind of again, same topic. If I start looking at if I consider linear system or system of linear equations, right? So how can I go from a system of linear equations directly to my matrix times a vector equals to a vector form, all right? Well, I mean, I can always do an intermediate step when I'm just looking at kind of linear combination of vectors. So my linear system, I can always rewrite as my first column, all of the coefficients of x1, 1 minus 1, 2, multiplied by variable x1, then x2 multiplied by all of the coefficients, x3 multiplied by all of the coefficients. I mean, kind of another way to look at it, what I could have done is I could have actually packaged this into vector equals to a vector, right? So if I had a vector with components x1 minus 2x2 plus 3x3, right, minus x1 plus 3x2 minus x3, 2x1 minus 5x2 plus 5x3, right? So if I'm looking at it as a vector with 3 components, I can actually just split this up, right? I can split up everything that has x1, right? x1 minus x1, 2x1, right? Using properties of addition of vectors, right? 2x2, 3x2 minus 5x2, right? And plus 3x3 minus x3 and 5x3. That makes sense? Right? Because if I'm adding vectors, it's just component-wise. So this one vector equals to sum of those 3 vectors. And then all I'm doing here is I'm basically just factoring out the constant x1. If I factor out x1 here, I'm going to get, right, 1 minus 1, 2, 1 minus 1, 2. Factor out x2, I'm going to get minus 2, 3, minus 5. Factor out x3, I'm getting 3 minus 1, 5, right? And on the right-hand side, this equals to my column vector 9 minus 6, 17. That makes sense? All right, so kind of going in between linear combination of columns to system of linear equations. And this and that is also equivalent to having a matrix times a vector, right? Because now that I have my columns of column vector coefficients of x1, coefficients of x2, coefficients of x3, I can package them all into the matrix and then multiply matrix by my unknown vector x. On the right-hand side, I have my vector b, right? So this would be like a very concise form of writing my linear system, right? So here I have 3 equations and 3 unknowns, but I mean, in real life applications, I mean, you normally use computer to solve those, but like if you're solving some differential equations numerically, you would have linear systems of like thousands and thousands of unknowns and thousands of equations. So you're not gonna write all of those. So it's really helpful to have a very concise way for writing something, right? So you can like define your matrix A somewhere, you can define your matrix B in some subroutine somewhere, but ultimately in the computer, when you're writing an algorithm, you would just be dealing with something really simple, like a matrix equation, right? An object A multiplied by object X equals to object B. All right, so that's kind of motivation between rewriting it in this form. That makes sense? Right, not too bad. Again, just kind of learning different ways of writing the same thing. All right, so let's do one little theorem here. So from what we've learned so far, so if A is an m by n matrix with columns A1 through AN, and B is an Rm, then, so M component vector. So the matrix equation, so just what we did earlier here, writing down all those matrix equations. The matrix equation have the same solution set as the vector equation, right? X1, A1, X2, A2. So it's, again, kind of restating things we just talked about, right? So looking at B as the linear combination of columns of A is really the same as looking at B as the multiplication of A formed by those vectors times the vector X consisting of those unknown constants in the linear combination. So kind of one extra more representation of the same thing here, just in terms of matrix multiplication. Right, and this in turn has the same solution set as a system of linear equations whose augmented matrix is, right, columns of A and B over here, right? So we're basically just adding one extra representation here, right? So I can say that my matrix equation AX equals to B, right, has a solution. All right, so kind of like one extra condition we can add here. So now we're gonna have four ways of looking at the same thing. Make sense? All right. But in practice, what you're gonna have to do is, I mean, you're gonna have to do a row reduction algorithm to solve, right? So you would always be going back to kind of taking columns of A or taking the vectors that span a space, augmenting it with the column B, and then solving it by row reduction, right? So again, in practice, it's basically connecting all of those other representations of the same thing to basically solving an augmented matrix. We're looking for solutions of the augmented matrix. So let's do examples. So for existence and, let's do existence of solutions. So if I'm looking at my matrix equation AX equals to B has a solution if and only if B is a linear combination of columns of A, right? So again, we're kind of restating the same thing as we did before. So if I had a question, right, I'm given a matrix A and given a column matrix B, right? Is the equation AX equals to B consistent for all possible B1, B2, and B3? Right? So again, you should kind of really start, like in your head, being able to make a correspondence between all of the different representations of this, right? So asking whether equation is consistent for different values of B is asking whether my matrix equation has a solution, which is the same as asking a question whether B is in the span of columns of A, or whether augmented matrix, if I do A in augmented column B, whether that has a solution, or kind of whether B is in the span, or B can be represented as linear combination of those columns, right? So in your head, you should get used to kind of, at the same time, thinking of all four of those conditions as being the same, right? So what do we do here? Well, okay, I know that really the only way to attack this is, because even if I started writing down linear combinations, right, and looking for C1, C2, and CP, what I would end up with is this augmented matrix that I have to solve. So at the end of the day, trying to solve it any one of those ways, I'm going to come back to doing it with the augmented matrix. So you might as well just skip to the augmented matrix way to do this. All right, so you can, all right, form the augmented matrix. I have 1, -4, -3, 3, 2, 2 and minus 2, 4, minus 6, and 7. And my last column is B1, B2, and B3. And so I found my augmented matrix A and augmented column B. Then again, to start doing your row operations, I have pivot here. I want to eliminate everything below. All right, so I'm going to do row 2 plus 4 row 1, and I'm going to do row 3 plus 3 row 1. All right, using first row, I'm eliminating minus 4 and minus 3. All right, so I'm doing all those operations, and it's fine that I don't know B1, B2, and B3. I can just write this down as I'm doing my operations here. So I have 1, 3, 4, and B1. I'm not doing anything to the first row. Then I have 0, 14, 10, and I have B2 plus 4B1, right? Row 2 plus 4 times row 1. And next one I have 0, 7, 5, and I have B3 minus plus 3 B1. Right, so row 3 plus 3 row 1. That makes sense? All right, so do I have more pivots? Yeah, I have another pivot here. So pivot column 1. The second row has a pivot, so I'm going to have first and second pivot columns for now. And I want to eliminate what's below the second pivot, so 7. All right. So here again, I'm not going to rescale. I'm just going to do my row 3 minus 1/2 row 2. All right, so 7 minus 1/2, 14 to eliminate 7. All right, so and from this, if I rewrite, I'm going to get again 1, 3, 4, B1. First column is the same. Then second column is also the same. So 0, 14, 10, and B2 plus 4B1. And then the very last third column, or third row, right, I'm doing R3 minus 1/2 R2. So I'm going to have 0, 0. 5 minus half of 10 is also going to be 0. And over here with my B's, I'm going to have B3 plus 3B1, right? This is an entry in my third row, minus 1/2 row 2. So minus 1/2, and the value in row 2, B2 plus 4B1. All right, that makes sense? So and now what am I looking for? The equation is consistent for all possible. So I'm looking for where equation is consistent, right? Is the equation consistent? So does this equation have a solution? So I'm asking whether this equation has a solution is equivalent to asking whether the augmented matrix has a solution or whether the augmented matrix is consistent. So when is my augmented matrix consistent? In this case, it's easier to really look at, I mean, where is it not consistent and which values of B do I need to exclude, basically. So where would this not be consistent? All right, I have pivot in the first column. I have pivot in the second column. So there's nothing really going wrong here. But if I look at my very last row, all right, because when I start translating it back to my original variables, I will have like 0 times x1 plus 0 times x2 plus 0 times x3 equals to, right, all of this stuff, right, B3 plus 3B1 minus 1/2 B2 plus 4B1. And in order for this to be consistent, I definitely need to have all of this stuff equals to 0, right? Because all of the coefficients are 0, I need this to be equal to 0 for consistency. All right. So if I rewrite this, I have B3. Maybe let's simplify first. All right, I have B3 plus 3B1. Here. So B3 plus 3B1 minus 1/2 B2 and plus 2b1 or minus 2b1. Now, so okay, I have 3b1 minus 2b1. So I will have b1 minus 1/2 b2 or minus b2 over 2, and then I have plus b3. So if this equals to 0, my system will be consistent. And if this not equals to 0, then I have inconsistent. All right, or no solution. All right, so my question was, is the equation consistent for all possible b1, b2, and b3? Right, and it looks like no, right? Not for all possible values, because if my b1, b2, and b3 are such that this sum is not equal to 0, my system will be inconsistent. All right, so not for all. That makes sense? All right, so let's do kind of summarize a lot of that stuff in this theorem here. So it's kind of like how the theorem is stated in your book, right? So we have kind of those 4 equivalent cases. So if A is an m by n matrix, the following statements are logically equivalent. So they basically mean the same thing. All right, so one is for each b in Rm, the equation x equals to b has a solution. All right. Second is each b in Rm is a linear combination of columns of A, then columns of A span Rm, and then we only have kind of like one new condition that A has a pivot position in every row. All right, so we'll kind of look at it, but again, kind of we're dealing with column vectors with forming a matrix, coefficient matrix out of those column vectors. So B is, right, a vector with components B1 to Bm, and X, well, actually this should be n, this should be n, right, because I have n columns. All right, so I kind of rewrote this in little diagrams. It's kind of a little bit easier to look at it. All right. So my condition A, right, saying that for each p in Rm equation has a solution, right? Basically, my matrix A formed out of the vectors multiplied by a vector X with m components. M equals to B. So if this has a solution, so I can find some values x1 through xn. In Rn, right, for each b. And this is equivalent to condition B. Here, each b is a linear combination of columns of A, right? This is saying if I take my vector B1 to Bm, I can rewrite this as a linear combination of columns of A, where my constant multiples are going to be my x1, xn from here. So those two are equivalent, right? And then condition C kind of equates everything to columns of A span Rm, right? So the span of columns of A is my R. I messed up all of this. Should be Rn, En, Rn. I have to rewrite this. Right. And the only kind of new condition here is A has a pivot position in every row. Right. So kind of to get a hang of it, understand why. I mean, here we're looking at not just whether we have a solution, but for each B in Rm, whether this has a solution. But remember, in the previous example, over here, for some B, so some vectors B, this is not going to be possible, right? So in this case, no, not for every B. But here we're looking at for each B. So any B, vector B you take, the equation has a solution. right? So for every vector B in Rm, the linear combination of columns of A, I can write it down as linear combination. Columns of A span my Rn. And now we're looking at the pivot condition, right? So remember when we were doing our row reduction. So if A has a pivot position in every row, what does that mean for us? That means that once I start taking my augmented matrix and doing elementary row operations, I end up with some echelon form, right? So I mean, B will change because I added, subtracted some rows, but I'm basically getting the equivalent system in echelon form. If I'm looking at echelon form, right? If A has pivot position in every row, then this echelon form will have pivot position in every row, right? So basically have something like, you know, pivot, 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 right, and so on. So in every row, I will have a pivot. And if I have a pivot in every row, that means that I have no free variables here, right? And also that means that I have no pivot in the augmented column, right? So I'm not going to have like the row of all zeros and the last entry is not zero, right? Because I just don't have this extra row here because I do have pivot in every column in A, right? Does that make sense? I can still have infinitely many solutions because I mean, I can, right, this could be a lot more unknowns than equations, but I definitely won't have a situation where I'm going to have kind of 0, 0, 0 and some non-zero value. That makes sense? Yeah. So if A has pivot position in every row, that would mean that I am not going to have a situation where I have kind of one row of zeros with a non-zero last entry in augmented column, which would be the only way that I would get inconsistent system. Does that make sense, guys? Yeah. And this condition about A having a pivot position in every row being equivalent to basically having my solutions, my system always consistent. That makes sense? Questions? No questions? All right. All right, so let's do example. Yeah, that one's pretty easy. So I have matrix A, I have column vector X, and I want to compute the product. So again, we're just kind of practicing new notation here. All right, so if I want to compute AX, I have 2, 3, 4, minus 1, 5, minus 3, 6, minus 2, and 8. And I'm multiplying it by x1, x2, and x3. All right, this is my AX matrix multiplied by vector form. So how do I do this? Remember our rules. I have columns, and each column is multiplied by each component in X. So I would have x1 times the first column, 2 minus 1, 6, plus x2 multiplied by second column, 3, 5 minus 2, and I have x3 multiplied by third column, 4 minus 3 and 8. All right. So if I put everything together, right, multiplying constants by vectors and then adding everything, I'm going to have 2x1 plus 3x2 plus 4x3 minus x1 plus 5x2 minus 3x3, 6x1 minus 2x2 and plus 8x3. Okay, that makes sense? So, and I mean, this is basically how we go from, if I had this equals to some vector b, right, with some components b1, b2, and b3. Right, I can either write this in the matrix equation form, ax equals to b, or I can write this in my system of equations form, where I basically have two vectors equal to one another, and I have 2x1 plus 3x2 plus 4x3 equals to b1, right, minus x1 plus 5x2 minus 3x3 equals to b2, and 6x1 minus 2x2 plus 8x3 equals to b3. And again, just two different ways of writing the same thing. So kind of last theorem here for this chapter. So basically, again, this summarizes how do we multiply matrices by vectors. Right, so it's called the row vector rule, basically matrix multiplication rule here. Right, if the product AX is defined, meaning my dimensions has to agree, right? In order for this to be defined, the number of columns of A must be equal to the number of elements in a vector, because I'm always doing it kind of like column by element. Right, this column times element 4, this column times element 3, this column times element 7, right? So for it to be defined. And AX is the sum of the products of corresponding entries from row I of A and from the vector X. So this basically gives us a fast way of computing this product. So instead of kind of doing this step where I'm doing 4 times vector 1 and 0, right, plus 3 times 2 and minus 5, right, plus 7 times minus 1 and 3. So instead of kind of doing all of those steps, I can just skip to my final step. Right, so what I will do is I will take 4 times 1, 2 times 3, minus 1 times 7. Right, because when I'm rewriting it, 4 times the first column, 3 times the second column, 7 times the third column, when I put everything together, I end up with, right, 4 times 1 plus 3 times 2 plus 7 times minus 1, right? And then 4 times 0 and plus 3 times minus 5 plus 7 times 3. And I put everything in one vector. So this row vector rule basically just tells you kind of the rule for multiplying this, kind of skipping those two steps when you're doing scalar by vector multiplication and then adding vectors together. So it ends up being basically you're going through your rows 1, 2, minus 1 and multiplying them by elements in X. All right, so I'm kind of following the rule. You would do column or row by a vector. So row vector rule. So going through the first row, 1 times 4, 2 times 3, and minus 1 times 7. Right, so kind of going through row times vector. And in the second element, again, I'm doing row times vector, 0 times 4, minus 5 times 3, 3 times 7. 0 times 4, minus 5 times 3, and plus 3 times 7. That makes sense? So again, all this does is just basically allows you to skip those steps and just go directly to the final step. That makes sense? Yes, if you compute this, you're going to get 3 and 6. All right, so again, over here, if I want to skip steps, is this product defined? If I'm always going row by a vector, So I'm gonna go first row, and the vectors will give me my first components. So I will have 2 times 4 minus 3 times 7. All right, first row times a vector. Then you go to the second row, and I'm going to do row times a vector. I'm going to have 8 times 4 plus 0 times 7. And then you go to the third row, minus 5 and 2 times a vector. So I will have minus 5 times 4 plus 2 times 7. Make sense? So let's go row times a vector, row times a vector, row times a vector. All right, so then you do arithmetic at minus 13, 32, and minus 6. Make sense? So we can do the very last one. So this one's pretty easy. And if you look at this is actually a special matrix that we'll talk about later. So we'll call this the identity matrix I. Identity matrix. So if again I do my row by vector rule, I'm going first row vector. All right, so I'm going to have 1 times R plus 0 times S plus 0 times T, my first component. Going to the second row, I have 0, 1, 0. So I'll have 0 times R plus 1 times S plus 0 times T. And the last one, I have 0 times R plus 0 times S plus 1 times T. All right, so row by column. So, but what I'm getting here is, because I had 1, 0, 0, I'm multiplying it by this column vector, this one in the first pivot position basically only leaves R, because I have 1 times R, the rest is 0. All right, so my vector is going to be R, the first component. Here I have 1 in the second position, so the only thing that survives is S. And here I have 1 in the last third position, so the only thing that survives is T. Right, so my result is RST. So, but if you look at it, I mean, what happened here? I had a matrix multiplied by a vector RST, and I'm getting another vector RST, which is exactly the same. So, and this is why it's called an identity matrix. It's basically an equivalent of multiplication by 1 in scalars, right? So 1 times some scalar, A is going to be equal to A. It doesn't change the value A. For matrices or for vectors here, my identity matrix multiplied by my vector X is always going to return back my vector X. So it's basically equivalent to multiplying by 1, right, for scalars, except this is now like, it's like a 1 for matrices and vectors. So it's called the identity matrix because it doesn't change the value of my vector, right? I had RST and I still have RST. That makes sense? So, and again, all we're doing here is we're kind of skipping those 2 steps where we have to multiply scalars to vectors and then adding vectors, right? And kind of skipping directly to the result. Make our life easier. And then the last thing is just some rules when we're dealing with matrix times a vector products, right? So if A is an n-by-n matrix, U and V are some vectors in Rn and C the scalar. So if I'm taking a matrix and multiplying by sum of 2 vectors, I can distribute my matrix A. And if I have like a scalar multiplied by a vector multiplied by a matrix, I can always factor out that scalar. So, I mean, we can just do this kind of with something simple, right? Maybe I have A11, A12, A21, A22 is my matrix A. Right? And if I multiply it by, say, like 2 vectors, U1, U2, plus V1, V2. All right, so I'm just taking like 2 by 2 matrix and 2-dimensional vectors. So why can't I distribute my A? right? I mean, we can add this and multiply by A, and we can compute this on the other side, right? So this is A times U plus V. So I have A11, A12, A21, A22 multiplied by U1 plus V1 and U2 plus V2. Now, first component, second component, using my kind of matrix multiplication definition, I'm always going row by column, right, or row by vector. So I'm going to get A11 multiplied by U1 plus V1 plus A12 multiplied by U2 plus V2, my first component. And second component, I'm taking my second row, multiplying it by column. So I would have A21 multiplied by U1 plus V1 and plus A22 multiplied by U2 plus V2. All right, so that's what I will get if I do A times U plus V. And then you can do AU plus AV, and you'll end up with the same thing. All right, so if I do AU plus AV, right, I have A11, A12, A21, A22 multiplied by U1, U2 plus A11, A12, A21, A22. Right, so it's basically just, I mean, you can do it for kind of 2 by 2 and 2-dimensional vectors. You can do it for arbitrarily large A and vectors. It's just kind of easier to see conceptually why this works at V1 and V2. Right, if I'm doing my row by column, I'm always doing row by column, row by column. Right, if I'm computing my products here, A11 times U1 plus A12 times U2, A21 times U1 plus A22 times U2. And over here I have A11 times V1 plus A12 times V2, A21 V1 plus A22 times V2. Now, if you add everything together, you're going to get the same thing as we had over here. Right, I have A11 U1, A11 V1, A12 U2, A12 V2. I can factor out A11 U1 plus V1. I can factor out A12 U2 plus V2. And over here, I can factor out A21 U1 plus V1 and plus A22 U2 plus V2. Right, and we have the same, right? This equals to that. So I kind of showed for the simple case that A U plus V equals to AU plus AV. It's kind of using our multiplication rules. And you can do the same with this, right? So I can multiply a constant by a vector first and then do matrix multiplication, or I can do matrix times a vector and then multiply a constant in later. And you guys can do this for practice yourself. But any questions so far? Makes sense? Not too bad, right? Yeah, like the hardest part here is again just kind of getting used to this new notation and like new ways of thinking of things. But once you get used to it, it's really not that bad. I think we don't have that much time. Yeah, we're gonna have to leave like chapter 5.1 mostly until next time. But I mean, we can start it a little bit. So like next chapter, I guess we'll have to do next week mostly. But what we're gonna start looking at is kind of more about solutions of systems. And we'll look at two different combinations here. So first we'll look at what's called homogeneous linear systems. And homogeneous linear systems are when kind of in a matrix equation form, you have A times some vector X equals to 0, right? So something like this. You have matrix A, and you multiply it by some vector x, but what you're getting for your vector b is just all zeros, right? So this is going to be called homogeneous system. And then we'll look at how solution of this homogeneous system relates to a system, a non-homogeneous system. Right, so my vector b is not equal to a zero vector. So that's what we'll do in 1.5. Right, so for homogeneous systems, you always have an obvious, it's called trivial solution as zero, right? Because matrix times a vector, how can I get a zero vector in return? Well, if I multiply a matrix by a vector zero, using my matrix multiplication, I will have, right, row by column, 1 times 0 plus 2 times 0 plus 3 times 0, right? 4 times 0 plus 5 times 0 plus 6 times 0, 7 times 0 plus 8 times 0 plus 9 times 0, right? This is all going to be just zeros, right? 0, 0, 0. Yeah, that makes sense. So your solution x equals to 0 vector is always going to be a solution of the homogeneous system. But the question here is, well, is that the only solution I have, or could I have some solutions that are not just those trivial zero solutions? Like, do we have non-trivial solutions, right? Do we have values of vector x that satisfies this equation that are not zero, right? And yes, we may have that, and the condition for that would be is I would have to have a case when I have some free variables present, right? So a homogeneous equation will have more than just the zero solution, or it has a non-trivial solution if and only if equation has at least one free variable. All right, so for this homogeneous system, I basically have two options. I either have a unique solution that's a trivial solution, or I have infinitely many solutions. All right, so I guess, we're kind of out of time today, but we'll do this next time. So we'll kind of look in detail at different solutions, X of homogeneous systems. And then we'll kind of start rewriting them as like linear combinations of different vectors and things like that. And then we'll also start looking at non-homogeneous systems and look at how solutions of those non-homogeneous systems related to solutions of homogeneous systems. Because if this X is solution of the homogeneous system, we'll actually show that for non-homogeneous system, the solution can be constructed using solution to the homogeneous problem, plus some other what's called particular solution to a non-homogeneous problem, right? Because here I'll basically have A times P equals to vector B, A times homogeneous solution equals to a zero vector. So then my kind of sum of those two, A P plus X H, will be equal to B plus zero, which is just B, right? So but we'll talk about this next time. It's kind of what you guys should look forward to. And I guess since we didn't really do 1.5, what I'm gonna do is, so I will post homework for 1.4. And your quiz 2 should have been on 1.4 and 1.5. I think I'm not gonna redo the quiz, but I'm going to move it out a little bit.
Sounds
Yeah, I'll move it out because so we'll do 1.5 next Monday. So I'll make a quiz due like over a week, like for the following week from that. But you guys do have your quiz. So what's posted is quiz 1. You should be able to do it now. There's like 4 problems. And they're all from chapter 1.1 through 1.3. So 1.1 to 1.3. So not what we did today, but what we did kind of the previous 2 weeks. All right, and your quiz two will be 1.4 and 1.5. So this one is due September 10. And this one was due September 17, but since we didn't do 1.5 yet, I'm going to move it out to like September 20 something. Yeah, like September, say 24. Yeah, so I have more time to prepare for it. That make sense?
Sounds good.
Yeah, so yeah, we'll talk about this next time. So, but yeah, but right now I have 1.1 through 1.4. You guys can do. Questions? No, everyone's good?
No, thank you, Professor. Have a good day.
Yeah, okay, no problem. Yeah, you two guys.
Thank you, Professor.
Thank you. Will you post the notes at the end of this?
Yeah, so I think I posted, yeah, I'm going to like shuffle things around on the on Canvas, but so the notes for today is part of the notes for week 2. So that's already posted, but I'll already post it in week 3.
All right, thank you, Professor.
No problem. All right, we'll see you guys next week.
Yes, have a good afternoon.
You too.